All right, let's talk a little bit more about transverse waves here. So again, transverse wave is the motion of the particle in the medium. The medium is the material that the wave is moving through. The motion of the particle in the medium is perpendicular to the direction of the wave. So if I have like this and I give a little pulse there, I'm sending a wave down. I just made a motion over here and the wave ends up over here. Now you don't see this nice slow wave moving along like that because this is real time. And also it's just a slinky and I got a small screen here. But as right now there's a little bit of longitudinal wave there as it's moving back and forth. All right. So again, if I just drop this hand right here, drop my right hand down and then up, well, this right here is going to move. I'm not touching this directly. So somehow this action over here gets translated over here. And so give a little bit more slack. And so wave propagation, and it ends up over here and this moves up and down. Now let's think about what's going on in a transverse wave. As I move down, I'm basically pulling. I am pulling on these coils right here. As it goes down, this coil is pulling on this coil. And as this coil moves, it pulls on this coil. And as this coil moves, it pulls on this coil. And as this coil moves, it pulls on that coil, and so on. So every time that part of the medium moves, it pulls another one with it. And that is key for transverse waves, is basically there needs to be enough tension or enough response as one object doesn't bump into it. As one moves, it pulls the next one with it. Now, why does this matter? Let's say there's an earthquake on the other side of the world. Well, these waves are sent, these compression waves and transverse waves are sent, shear waves, are sent from wherever the earthquake is to the Richter, the earthquake machine. Talk to the geologist. Seismometer. Gets to the seismometer that, well, you basically have the earth right here. If I've got an earthquake happening at the thumbs and my seismometer is up here, well, how does the wave get there from one side to the other? Well, some waves are going to travel right through the Earth's core, and some waves are going to be traveling the long way around along the crust of the Earth. This is an important clue about what's in the middle of the Earth, because transverse waves require, if I move one molecule this way, it's going to pull the next one with it. Well, that works in solids, great. Kind of works in liquids. In gases, no. Plasmas, no. And so, or if it does propagate, it doesn't go very long. Just imagine you're in the tub and you push down on the water. Well, you see the ripple on the surface very quickly, but that ripple doesn't stay there. It eventually sort of levels out. And part of the ripple there is from compression waves. So this gives us the clue is that, again, got my world here, earthquake down here, seismometer up here, and it turns out that the compression waves show up here faster than the transverse waves. Well, let's come up with an explanation for that. Well, compression waves get there faster, not because they're traveling faster, but they don't have as far to go. Because compression waves travel through the center. Because compression waves travel in gases. Otherwise, you would not hear any sound at all. Because all you need is one set of molecules slapping against another set of molecules, which slaps against the next set of molecules, and so forth. So you get this sort of... It works great in my head, whether the visual is there or not. Transverse waves require an interaction between the two. Not just slapping into it, but the pulling. Because the transverse waves take longer to get around to the other side of the world, the middle must be something in which transverse waves don't travel very well. And that way we knew the Earth wasn't solid. And this was the key piece of information in trying to determine the geology. Then you go through a whole lot of fancy mathematics that I frankly haven't done because I don't do geology, but you go through a lot of fancy mathematics in geophysics, and eventually you end up with, well, you can start coming up with, not only can you come up with, the size of the Earth, but on a smaller scale, you can actually start figuring out what is underneath. You can come up with the density of the ground underneath to actually explain how long it takes for the wave to get from one spot to another. When my wife was doing her graduate research, she was working in the Bad Creek area of North Carolina, where they were putting in a new dam for basically storing energy. That's a different story. And in order to clear out this reservoir that they were building, they would blast it. And so because the timing of the blast was known, all we had to do was set up seismometers all around the area. The blast would happen. We could then figure out, we would know the time at which the seismometer caught the signal, and we can start to, she could start to piece together the geology in that area. It was actually quite fascinating. I was there just to drive around and keep her company, but yeah, all that fancy geo stuff, that was her. So anyway, transverse waves, a little bit more detail.